So the new topic under the heading of the chemical kinetics is the methods for the determination of order of reaction. So there are basically the three methods we are going to discuss in this syllabus. And the first one is called the integration method. And according to your syllabus, we will only discuss the zero order reaction. And we are not going to discuss the first, second, third, and there are a lot of things under this order of reaction. So this is a very basic information to understand the zero order reaction. But the method is called the integration method. The second method will be the graphical method, and third method would be the half-life method. So today I'm going to finish the first one, which is the integration method, and specifically the zero order reaction. So why it is called the integration method? Because we are going to use the mathematical operation that is called the integration, and that's why this is called the integration method. So this is the actually the final equation of this one. So I am using the whiteboard to explain you how this equation is coming out to the final equation, and then I will move again to this slide. So let's suppose there is the reactant A, that is converted into the product. So this is the one of the simple reaction. Any reactant is converted into the product. A mean you can consider any of the reactant. Like in the previous case, we discussed the water is having a zero order action. That means you can do the same process for the water to confirm the order is the zero order action. So the first thing is the what would be the rate. Again, there is the repetition of the previous knowledge which we have already discussed. The rate is proportional to the concentration of A, and this rate particularly is the product, as we have detailed discussed in the previous lecture as well. So that means this is the formation of the product is proportional to the concentration of A. More will be the concentration of A, more will be the product. So this is in the equation form what we have written over here. So this rate you may write in the form of the product as well as in the form of the reactant. So rate of reaction, if I want to be discuss the rate of reaction with respect to the reactant, and as you know, this is going to be disappear with respect to time. So I am putting the sign minus. So this would be the change in concentration of A, and this is the A with respect to change in time. So this is the rate of fraction with respect to the A, and this is written over here because this is being decomposed and this is written with the sign. So you can also write the P is proportional to the concentration of A. That means more will be the reactant, more product will you will form, or in you can also write with this statement. And again, I'm going to explain. More will be the concentration of this, more will be the disappearance of the reactant. So this is with the product. When the concentration of reactant is more product will form or more reactant will disappear. So that means this is the disappearance of reactant A with respect to the concentration of reactant. More will be the concentration of reactant, more will be the disappearance of the reactant. That means the more will be the decomposition of the rate of with respect to the reactant A. So I am going to now derive very simple way. There is no complicated mathematics over here. So for the other students, other than the chemistry, they also can learn easily how we are going to integrate this equation. So that's why this is called the integration method. So again, if you remove this proportionality sign, there should be the constant at the right hand side, and that called the rate constant. Again, I'm writing this equation A and divided by time. Now this is equal to K and the concentration of the A. So here just I have removed this proportionality sign to put the constant over here, and that is called the rate constant. And again in the third equation, maybe you can do yourself. I am just rearranging over here. So if you multiply this whole equation with the minus, this minus will become plus. There is no need to write over here the minus, and you can put the, sorry, okay. So you can put the minus with the other equation, and I am putting over here. Let's suppose now this will become a minus, and this is, or you can say you are just shifting this minus toward this, so you are moving this minus to here. So this is the another equation. So first, second were there, and third is the this equation. Now I am going to integrate over here. So this is the sign for the integration. Again, one by one, if you are taking the notes, it's better you will understand all the steps, because it will be difficult for me to write again the same things. So I am using the whiteboard. So I'm just directly putting over here. So this is the sign for the integration. And that means now I'm going to integrate this form, and also to integrate the this, that is the this is the, let me first correct, this is complicated over here. So the first I'm rearranging again, d a, okay, and moving this dt to the other side, and okay, and this is the k little. This is because in the denominator, if it's going to divide, I'm just putting it on the right hand side, it will multiply by this one again. And this is the a, what is written over here. So just there is the just rearrangement of the equation. Now here, because this is the zero order reaction, and one power of any of the reaction is zero, that would be equal to 1. So there is no need to write over here. So your final equation will become, again this is the sign is missing over here, this is the minus sign, d a, and equal to minus, I'm just putting k before, and dt, okay, just rearranging this one. Again, there is no difference between this equation, and this equation. This is just the rearrangement of the equations. Now I'm going to integrate with the sign, and let's suppose this is the long summation sign for the integration. That means you are going to integrate the variable, because the time is changing, and there is the change in the concentration of the reactant. So there is the first formula of the integration. This, if you integrate any of like this dA, dB, dC, so this will give you the integration of the A. And in a similar way, minus K, we are not going to integrate the K, because the K is the constant, so it is not to be integrated. So you can only integrate which are the variables. So time and concentration are the variables, that's why you are going to integrate. So in a similar way, if the integration of dA is A, of course the dt will be the t. And if it is a dB, of course the integration will be the dB. If there is a dx, the integration will be the x. So this is a very simple and the basic formula for the integration. So I think there is no any difficulty to understand this one. And plus there is the constant, according to the mathematics, there is the constant from the right hand side. So I am integrating this one to this will remain the same, dt will be t, and there should be the constant on the right hand side, c is the constant. And now we are going to get the value of this constant. So actually we are assuming over here is the constant. No, but as a chemist, we should know what is actually this the constant. So how can you calculate the value of the constant? So we are assuming here, let's suppose if the time is zero, look at, if the time is zero, that means what would be the condition over here? That means if the time is zero, the reaction is not started yet. So there will be the initial concentration of the reactant. So there is no formation of the product, only there is the reactant, and the reactant will be at its initial concentration. So that means if time is zero, then your A, which we are going to use as a reactant, that will be the initial concentration of the reactant. I'm just differentiating with the A naught to differentiate between the A and the A naught. This is the initial concentration, and this is the concentration at any time. So what time is there? There should be it may be minute or the second, but there is only one value. That means when the time is zero, that concentration will be equal to the initial concentration. So now in the second uh, uh, equation, the next equation, I am putting the value of C in this equation. So when you put the value of C in this equation, now this equation will become like this. I am replacing the equation over here. So just putting the value of C, C is the A naught. So what would be your next equation? Next equation would be A, that is equal to minus KT plus and initial concentration of the A, that is the value of the C. So you have calculated the value of the C, and this is the equation. And look, this is the same equation I have shown in the previous slide. So I'm moving to the again to the, so this was the equation, and I started with this one and ended with this one. I have shown you how to integrate this equation. So this is the final form of the equation. You can say only this equation is for the zero order reaction. Now I'm going to confirm or explaining how uh, the integration method is used to determine the order of the reaction. So this is just the statement now I'm making out of this equation. So again, this is the concentration of A at time t. This is the concentration of A at time 0. And this is the rate constant. And here you can say this is the rate constant for the zero order reaction. So now you can differentiate the rate constant with labeling with what is the order of reaction, because this equation is only for the zero order reaction, and that's why the rate constant, this rate constant will be the for the zero order reaction, and t is the time. Now, how can you determine the order by using the integration method? So this is the actually the explanation. And if k remains the constant by putting any of these value, then the order must be a zero order reaction, because only this equation in the universe, only this is the equation for the zero order action. This is not for the any fractional order action, first order action, second order action. This is only for the zero order action, and this is the rate constant. That means at any of these value, when you put the values, then you will get the same value for the rate constant. And if you get the same value for the rate constant at each time, that means the order with respect to reactant A is the zero order reaction. So this is the final statement over there. So I am finishing with the units, and then I will take your questions. So what would be the unit of the rate constant for the zero order reaction? Look at the value over here, because at the start this is the rate equal to k concentration power 0. If it is the power 0, that will equal to 1. That means K will be equal to the rate. So for the zero order action, only for the zero order action, the unit of the rate constant is same as the unit for the rate of the reaction. And you know what is the unit for the rate of the reaction? It is a change in concentration per unit time or molar per second. So rate and the rate constant is having a same unit for the zero order reaction. And this is our all about our today lecture, how to determine the order by using the integration method.